Good morning, Jake. How you doing?
Good, how about you?
All right, thanks. So all we need is Karen. Good morning, Karen.
Wow, that's a really long way. Holy cow. Alright,
Vanessa, how are you?
Good, thank you for your email.
Oh, sure. Beautiful music.
Thank you.
Okay, we have 8:30. Let's get started. Good morning, Psych Stats.
Good morning.
All right, that's a really great response. Thank you all for your TED Ed responses. This is going really well. I'm enjoying reading about what you have to say, and we do like to distribute our practice very much. We might remember that from the first day of class, we talked about that book called Make It Stick. I think we introduced that on the first day of class, and that was this book that is getting a lot of favorable responses from faculty everywhere, and we're encouraged as faculty to get our students to distribute their practice, and we do that very much by using TED Ed, where we get you to respond to questions ahead of time, talk about it the next day, very much like somebody who practices for a rehearsal and then shows up to the orchestra rehearsal ready to go. So we're hoping to do that with TED Ed, and so far it's been going really, really well. So thank you all for your good participation there. I also want to say thanks for a good conversation the other day in our Journal Club session. Melanie was the star of the show, and so we already have Melanie out there on our Blackboard page in case you want to take a look at that video. And here's our schedule. We have Sarah up next. We'll just check in if Sarah's okay with that. And if you haven't already done so, you can make sure that you're double checking your date so that you are well established for that Monday and ready to go. Remember, this can be an article of your choosing. I encourage you to choose wisely. This can be a really great stepping stone for you if you're thinking about graduate school and you're thinking about getting into a particular lab or a particular line of work in graduate school, maybe within psychology or a related field, and you want to get some practice presenting some of that material. This is a great practice opportunity, and again, everybody can be videoed if you so choose, and that's entirely up to you. And then after you're videoed, what you do with that video is entirely up to you also. But that's the list that we've seen a couple of times. Just want to make sure people are okay with their particular dates. Okay. By the way, it looks like we'll be finishing up with these anyway on 11/9. On 11/16, the plan for the moment is to have one of my current mentees, so to speak, from OSU. There's a program called Preparing Future Faculty. So students who are just a couple years older than you, maybe they're in graduate school right down the road. We have Ohio State's graduate school. They have a very nice psychology program, one of the top-rated programs in the country, and I'm working with a student in that program who would like to at some point be a faculty member, perhaps at a liberal arts college. And her name is Ashley Brown, and she does some very interesting work in social psychology on narcissism. And I think Jake attended one of her talks over the summer. We had her in very briefly. She's going to be joining us on 11/16, and that'll be the last Monday that we have before we go off to the Thanksgiving break. Okay? So we have all of you on track for each of those Mondays, and then a graduate student will be visiting us thereafter. Okay? Okay. So One other idea about Monday is that on Monday, after Sarah, or I guess before Sarah makes her presentation, we're going to have a journal club session that'll feature chi-square. And chi-square is what we're going to be talking about on Friday's class. And then we'll have the journal club article that features some chi-squares in it. And it's really a favorite of mine for a couple of reasons. First, one of my favorite students from way back when, her name is Erin Colbert White. And I had Erin in Psych 200 and then in Psych 370. So she's a graduate from this room twice. And a Denison graduate. She was in Hannah's seat in Psych 200 and in Karen's seat in Psych 370. And not only that, but she has worked with a very, very charismatic African gray parrot. And if those of you who are unfamiliar with African gray parrots would like to see one, that's what an African gray looks like. And her African gray is called Cosmo. And I call him affectionately, or actually it's a she, I call her affectionately chi-square Cosmo, because in this particular article where we're analyzing chi-square, Cosmo's behavior, we're going to use chi-squares for that. So Erin Colbert White, a graduate, will be sharing with us chi-square Cosmo on Monday for the first half hour, and then Sarah will have her presentation. Okay? And on Friday we'll have a whole bunch of TED Ed questions on Friday for the chi-square chapter, which is chapter 13 in your books. Okay, so you can start reading that. For tomorrow, we will not have a TED Ed. We'll take a little break from that. And tomorrow, we're going to spend the entire time hands-on. And we're going to spend the last 15, maybe 20 minutes today hands-on doing some practice to get us set up for next Thursday's quiz. It'll be our first computer quiz. We've been on the computers a couple of times, but not a lot. So we'll get some practice today, all day tomorrow, and probably most of the session on Tuesday and maybe Wednesday of next week. Okay? Okay, so that's where we're going. Okay. Any questions on any of that? Okay. Fortunately, we're right on track with the syllabus. So what I'd like to do, as I always like to do, is try to take 2 steps forward, but first 1 step back and do just a little bit of review. So what I think we'll do this morning is something that professors occasionally call a think, pair, share. We'll simply call it a pair, share. I'll put you in pairs, and I'd like you to think about 2 questions from a relatively recent conversation that we had. On Friday, we were talking about hypothesis testing, and we were talking about some of the logic that underlies it, and some of that has a formal Latin name. Different kinds of structures, logical structures have Latin names. So what I'd like you to do is pair up. Why don't we have the 2 of you be a pair? Maybe you 2 can be a pair. Can we have you 2 be a pair? Can we have Sarah and Jake be a pair? And we'll have you 2 be a pair. We'll have those pairs get together and just spend a couple of minutes talking about what was question 8 from last Friday's TED Ed, and that was on this issue of affirming the consequent. There's a logical error called affirming the consequent, and yet it's somehow related to modus tollens, which was another one of the structures that we learned about in that TED Ed. So we'll ask you to think about modus tollens, we'll think about the logical error of affirming the consequent in your pairs, and then we'll see what you had to say. So please feel free to move your chairs anywhere that's comfortable for you. We'll give you a couple of minutes to chat with each other about that, okay? And then we'll see if you can share that with the wider group. Okay, so the questions are, what is modus tollens, and how is it similar or different from affirming the consequent? Go ahead. There's question 8, just in case you need to see it.
If we deny, if we Deny the consequence. So we said, oh, they're not playing. Okay, so they're violated.
Oh, like hot, yeah, yeah.
If you're already through with that, maybe you can generate an example or two of affirming the consequent. Okay, the logical error of affirming the consequent. Let's see what kind of creativity we can get on generating that type of logical error. Okay, hopefully people have had a chance to think through modus tollens and affirming the consequent, maybe generate an example, which is hard to do sometimes early in the morning, but why don't we see if somebody can remind us first about modus tollens, which is a correct form of reasoning, and the type of reasoning on which hypothesis testing is based. Somebody help us out with modus tollens? Okay, thanks, Karen.
So, like, if you know that if P then Q,
Okay.
then you know that not Q, or that not Q.
If P, comma, then Q. Let's go just that far. That's a proposition. If P, then Q. And what we might say then is, what do we call this first part? That is a fancy name. But yeah, the antecedent. Okay, this is the antecedent. If that's the antecedent, what's this other one? The consequent, okay? So the antecedent comes first, the consequent comes later. So Karen got us started very well, right? This is modus tollens. I put an MT up here. And sometimes in formal logic, they will abbreviate that way, MT for modus tollens. The alternate structure was modus ponens, which we actually don't use. But if P, then Q. And then we had a second line in our 3 lines of logic. What was that second line? You had it a moment ago.
So where not Q, then...
Okay, then not Q. And sometimes in logic, they put that little squiggle as a not. Okay, so here's our first statement. Okay. If P, then Q, we do an empirical investigation and we find out that it is not the case that Q is true. So we've negated the consequent. We haven't affirmed it, we've negated it. Okay. And then 3, they sometimes use this symbol. They use 3 little circles. And that stands for therefore. And what's our big conclusion? If P, then Q, not Q, therefore, not P, right? Okay, we can say not P. And that's how you would have the structure. So in our hypothesis testing, we might say if the null hypothesis is true, then the observed alpha level, right, the observed p-value would be greater than 0.05. We conduct an investigation, we look at our stats, we get a p-value that is less than or equal to 0.05, and that allows us to say we can reject that consequent, we can negate that consequent, and therefore we can say we can reject the null hypothesis, okay? Not P. If the null hypothesis were true, the probability of obtaining a particular outcome would be greater than 0.05. It is not the case that it's greater than 0.05, it's less than or equal, then we can reject the null hypothesis. That's the structural basis for what all the sciences do when they engage in hypothesis testing. People okay with that? Does that work for us? Okay. Right, so that's the structure. Now, throughout this semester, we'll occasionally come back to it, and we'll see some challenges to this, but that's the structure. So that actually works, and that's called modus tollens. It's a way of denying the consequent. Then there's a logical error called affirming the consequent. Okay, can somebody help us out with the conversation, or maybe you want to share the conversation you had about affirming the consequent? Maybe you had an example? Yeah, okay, thanks, Melanie.
Well, if we're consequent, we can't, and we basically find out that the consequent is true, we can't necessarily infer anything about the antecedent.
Okay.
So the example that I had was, if a person goes to the gym, then he or she will be sweaty.
Okay.
But if the person is found to be sweaty, it doesn't necessarily mean that they went to the gym.
Okay.
They could have gone to a sauna, or they could just be perspiring because it's hot outside.
Okay, right. Okay, so very nicely stated. When we begin to affirm the consequent, okay, that in and of itself does not permit us to go back and affirm the antecedent. Okay. Now we could get lucky. It could be the case, as we said, I think last Friday, that the person who is sweaty really is sweaty because she or he happened to be working out in the gym, but they could be sweaty for other reasons. Staying with Melanie's example, right? Okay. Here's another one that I think people really appreciate. Okay. And it brings us to yet another kind of a fallacy. But you might accept the truth of this statement. I have a lot of students, and I've been here for now, this is my 15th year, okay? And every once in a while, some fraction of our students at any college will be pregnant, okay? So, if a student is pregnant, then that student is female, period. How many people will accept the truth of that statement? If the student is pregnant, then the student must be female. Is that true for our species? Okay, it's generally true for the mammalian species. It's true for a lot of species. Okay, right? Okay. So if the student is pregnant, then that student is female. We have our antecedent, we have our consequent. Okay, so far so good. Hey, look. Sarah is female. Therefore, Sarah is... We affirm the consequent, right? The consequent, if somebody is pregnant and they're female, we affirm that Sarah is female. Therefore, what do we conclude? Can we conclude that she's pregnant? Okay, we can't conclude that she's pregnant. Now, it could be the case that she or a particular female, but you can't necessarily go back. It could be true, but it doesn't follow of necessity. Who's following that? Okay? All right, so we might even do something like this. We might say, a very different kind of a structure. I'll go to Venn diagrams now. I'm going to make P here for pregnant. That's the population of all pregnant people. And then here, not drawn to scale, is the population of all females. Okay? If we conclude that somebody is female, they might also be pregnant, but there's a good chance that they're not. Okay? And we can't go back and forth between these as if they're absolutely the same as each other. Right? If you're pregnant, then you're female. So far, so good. But if you're female, it doesn't necessarily mean that you're pregnant. And that kind of error is an error that we would call affirming the consequent. Okay? This particular case that I've drawn here in Venn diagram has another name, a related name, that is sometimes called the confusion of the inverse. Okay? The confusion of the inverse. You might make a note of that. It's related to this idea of the logical error of affirming the consequent, the confusion of the inverse. It is certainly true in my diagram that all P are F, but it is not true that all F are P. Okay? And when we make the mistake that we think, oh, because all are F, therefore all F are P, we've made a confusion of the inverse. You can't always flip these things around. Now, there are particular kinds of variables that might actually be reversible like that, but a lot of them aren't. Okay? And a lot of us, myself included, even though I've been teaching this formal logical structure for many, many years now, we, in everyday life, slip into these confusions of the inverse, these errors of affirming the consequent. You'll hear them all the time on television. If you're watching political pundits argue back and forth, sometimes they're doing so in play. Often they make these kinds of logical errors. Okay, so a little bit of formal logic to underscore the hypothesis testing that we've been doing. All right, so why don't we then move from that, unless we have any questions on the confusion of the inverse, or affirming the consequent, or modus tollens. Okay? Some of the logic underlying our hypothesis testing. Why don't we move on to the work that we had for today, and we'll see if we can put you into some pairs. And you are doing today such things as the distribution of means, and you also talked a little bit about confidence intervals. and the central limit theorem. These are some of the basic ingredients for hypothesis testing, particularly with means. And there are lots of questions on the distribution of means. So why don't we start out this way? Can you get back into your pairs and spend a few minutes talking about the first 3 questions? I'll project them for today's TED Ed. Okay, now that we've taken a step back, we'll try to go 2 steps forward. And today's TED Ed again was on the DOMs, and then toward the end of that you got into confidence intervals and central limit theorem. So questions 1, 2, and 3, they are, in your own words, briefly explain what the distributions of means is, identify the 3 characteristics of the DOM, and try to relate those to the statistical moments that we talked about last time. We got up as high as 4 statistical moments for any given distribution. And then the question number 3 would be, why would the DOM typically be less spread out or have a smaller SD than the distribution of individual scores in the population? So I'll project those up here, and you and your partner can chat about those. We'll go to questions 1, 2, and 3. Oops. Okay. Question 1, in your own words, briefly explain what the distributions of means is. Okay. All right, go ahead, mix it up.
Hi again. I know I did it. Yeah, like I don't know why I didn't say it. Yeah, if you like take like a population, okay, we're gonna do like Denison students or whatever. That wouldn't be the same like population. If you just said that you wanted to do all Denison students, it would just be a random sample from like all Denison students, and then another random sample from all Denison students, and another random sample. Right. Oh, question 2. Yeah. This is what mine is. So like, So oh, that was for question, I don't know, the other side was like,
that when like just this population, like you guys teaching all the means.
I basically found like, I've looked at it in the book as far as like, the mean of the distribution of means is the same as the mean of the original population. Variance.
Okay, I think people are making eye contact with me like we're done, so that's actually helpful. It's good to get the visual feedback like that. Okay, so why don't we go to question 1, and we'll see if somebody can tell us in their own words what the distributions of means is. Anybody want to help us out with that? Actually, a fairly weird concept, the distribution of means. Okay, thanks, Victoria.
So the distribution of means is a distribution of a collection of means from various samples.
Okay.
Samples from the same population.
Okay.
And so the means from those samples are put together in one distribution.
Okay. Yeah, very good. And one simple example that we often take is, let's say we wanted to measure height on this campus. I can bring in from the 2,200-ish students across the campus, I can bring in 20. I've got 20 seats here and 20 computers. I can bring in any 20 randomly selected. I can measure their heights, and somebody's going to be on the short end, or some of those students will be on the shorter end, some will be on the taller end, but they will have a mean, okay? And I can let those folks out and bring in the next 20, and I can get another mean, and I can get a third mean from a third sample and a fourth mean, and I can put now a distribution together of the means. So typically we think about distributions containing raw scores, and that's perfectly reasonable. And many of our distributions do contain raw scores. So Gwen's height would be a raw score, Karen's height would be a raw score, my height, Jake's height would be raw scores. And we typically have these samples, right? Maybe we really want to know about the population, that's a little bit too unwieldy, but we have to engage in abstraction to get some kind of a usable representation of the population. So we work with a sample, and we can take that mean, we'll get the first one, the second one, the third one, and we create a distribution of means as opposed to a distribution of raw scores. Okay? Who's okay with that? Is that working for us? It's kind of weird, and I don't think you talked about that in research methods. How many people did not talk about the distribution of means in research methods? Okay, so sometimes, certainly the distributions of means would have been relevant, but at Psych 200 level, students don't need to know that much about statistics, as you will here in this course. Okay, so we have the distribution of means as a distribution that contains sample means from the targeted population. Okay, identify 3 characteristics of the DOM as they relate to the first 3 moments. Can anybody help us out with that? Some characteristics of the DOM. Or if you just prefer to start with the first 3 moments, that's fine. Hannah's got something.
Yeah, so for the first moment, the mean of the DOM is about the same as the mean of the population.
Okay, right. And by the way, this is what we really want to know about, right? As scientists, we want to know about this. Maybe Melanie is interested in things like anxiety and whether there are gender differences. So she's really interested in the population. She has to work with a sample. This DOM is kind of a linking idea. It allows us to go from here to here, and Hannah is correct that we presume, a presumption in statistics is that the mean of this is comparable to the mean of that. Okay? So that's the first of our moments, right? And the moments speak to the shape of the distribution or how they're arranged. Something else? So that was the first moment, right?
Yeah, and then the second one, for variance, I said that the variance of the distribution of means is the variance of the population divided by the number of individuals in each sample. Okay.
Okay, real good. All right, so we're going to spend some time today, in just a little while, talking about variances and standard deviations and so forth. Okay, real good. All right. Did you have one last comment? Okay, what's your third moment? Yeah.
And then for the skewness, it's about normal if there's more than 30 individuals or if the population in each sample.
So typically, once you get up to about 30 or so, you'll find that this thing starts to smooth out and become pretty symmetric, and so it's going to have a skew of about 0. Okay? And probably, we could have gone up to the fourth moment, we'd probably have a kurtosis that's going to be approaching 0 also, which is an average level of thickness of the tails, but our book doesn't actually go into that level of detail. Okay? All right, so that's what we have. All right, and then question 3, I wonder if somebody else can help us out with this. Sometimes people find this intuitive, sometimes my students don't find question 3 intuitive. Why would the distribution of means typically be less spread out or have a smaller SD than the distribution of individual scores in the population? Maybe it's intuitive, maybe it isn't. Anybody want to help us with that? Melanie's got something.
So I basically said it's because the extreme scores are basically moderated because you're taking the means of all these different samples. So basically all the extreme values there are going to be less extreme values on a distribution of means.
Mm-hmm. Yeah, nice and slow. Okay, so if we go back to our example, you can imagine that we can fill this room with 20 Denison students, you can imagine that I would have been a college student and filled in that sample at some point, and particularly as males go, I'm quite a bit shorter than average, right? So I have something of an extreme score if this is the height distribution. Tall people up here, or we'll stay with men. Tall men up here, shorter men down here. I'm going to be very close to that extreme. Okay? I occasionally find people, adult males, shorter than me, but not too often, right? So I'm down here. But remember, I'm going to be one of 20 students in that particular set, okay? There could be somebody shorter than me, but probably not, or there wouldn't be many of them. And a lot of them are going to be taller than me. There might be a couple of extremes over here. When we average those out, we tend toward the central portion of this, okay? As that becomes our new score, that winds up in this distribution. And every once in a while you get a slightly taller sample or a slightly shorter sample, but remember that you're taking the means in all those cases, and that tends to mitigate those extreme values on either end. So we wind up with a relatively narrowish distribution. Okay? So they're all similarly shaped, presumably. If we had really good sampling, we would have something like a normal distribution in all of them. Then we have very similar means, but this one's going to have the narrowest of the standard deviations. Okay, real good. One other idea. Can somebody help us out with we have a special word for the standard deviation of this distribution, and what is that? Yeah, thanks.
The standard error.
The standard error, right? Okay, the standard error. Okay, and sometimes, and you'll see this often in all kinds of science journals. You'll see that the graphs will have a little legend that will say something like the error bars refer to the SEM, the standard error of the mean. Okay? Sometimes they'll even call it the standard deviation of the sampling distribution of means. Okay, so it goes by a lot of names. But we typically call this a standard deviation for the sample. And then there's a very special type of standard deviation that pertains to this very special distribution, the distribution of means. Its standard deviation is called the standard error. Okay? Right? So, and that's kind of the next question. It's conceptually similar because it actually is a standard deviation of sorts. Okay, so in meaning, it has the same idea, the average extent to which one of these scores departs from its own mean. But one of these scores, again, happens to be a mean. Right? This is a collection of mean. It is a distribution of means. Okay? Okay, and can somebody help us out computationally? How do we get there? How do we get to the standard error of the mean? So one of the questions in that set was, what is it conceptually? It's like a standard deviation. What is it computationally? Okay, Victoria's got it.
To find the standard error, you take the standard deviation of the sample and divide it by the square root of the sample size.
Okay, right. Okay. So as your sample size is growing and growing and growing, then you're still going to be taking the square root of it, but you're taking the square root of a larger and larger and larger number. So your denominator is getting bigger, and that means the absolute value of your standard error will be getting smaller. Right? Very, very simply, if we have